basic thing that motivated me to start this class, other than a little curiosity about how it would go, is that we found that in explaining our work in fusion to potential investors, to the general public, one of the things we've run into very early on is the fact that people just not familiar with a lot in modern science, and certainly a lot in physics. And a lot of what they learn from the mass media isn't even right. So I wanted to get some idea of whether we could have a discussion class, not a lecture class, to actually historically elucidate the development of physics. Because I've long thought that physics for non-physicists is taught very badly. I mean, when I was at Columbia a long time ago, we had a course that was similar to what people have mentioned. It was called Physics for Poets, colloquially. And it wasn't very popular. And the fact was, it was sort of just watered down Newtonian physics. And I've always thought people could learn a great deal about physics and science generally from a historical perspective, from how science developed, how it interacted with society. So that's basically what we're going to try and do. And that's what we're starting with. Now, this is an experiment. You're part of an experiment, because although I've lectured a great deal on subjects like this and in videos and in person, I've never led a discussion study group. So this is a new experience for me too. In my own education, I did go to a private high school, Phillips Exeter, which prided itself on having discussion groups rather than lectures. We actually had a standard class size of 13 students, all sitting around the table. So as a student, I had some experience with this a very long time ago, but not as a teacher. So what I'm trying to start with is the basic questions of what we're really studying, which is, what is science? What is the scientific method? And what is physics? And I can say that the scientific method was not something that I can remember being taught explicitly, either at Columbia or even in high school, or in graduate school. So that's the first question I want to start with. Starting with what's described in the readings, but adding your own opinions, I'm going to put out the question, what is the scientific method? And specifically, in reference to the readings about the reading from Alfvén's work, what is the key points he's making about the scientific method versus the Ptolemaic method? So I guess the way we're going to run this is I'll start by asking for hands up, but I might ask additional questions of specific people. So just use your little hands up. Where is it? It's down at the bottom under reactions, right? So just use the reaction button and raise your hand to speak. Oh, come on, let's not be bashful here. All right. Well, I will start. Layla.
Actually, there are some hands up right now, but I didn't raise my hand.
I don't, okay, now I see hands. All right, we'll start with Alex and then go to Layla.
Okay, well, my understanding of the scientific method is basically starting from observations. You do testing and then you create a hypothesis that you think explains what's happening. And then you do experiments to try to confirm or deny that hypothesis. And then based on the results of those experiments, you adjust your hypotheses and repeat. So that's kind of the way I look at it.
Okay. Well, let's go. Let's get some more hands. Sam and then Layla.
Yeah, to build on that, I remember like learning about the scientific method in like 6th grade, and it was like you do an experiment and you do like a little lab experiment, and then you come up with a hypothesis of what's going to happen, and then you like use that to make predictions, which I think is like what Alfin was talking about and you were talking about in part of your reading, where it's like the scientific method is like a tool that we have for sort of like, I don't know, like giving us direction, I guess, versus like revealing the ultimate truth about the world or something. It's like building like a set of rules and like a toolkit that we can use to like make scientific discoveries and technological innovations. But yeah, it's very like very procedure based. Like,
okay, Layla, you want?
Yes, from what I remember, the scientific method is a process to prove a certain theory where it's based on repeated measurements, repeating the same conditions and expecting the same measured data points, whatever you're measuring. That's what I remember of it being scientific method.
Okay, Peter and then Martin. Now, Peter, you're still muted. Peter, unmute yourself.
Yeah, sorry. I was just going to add the, I believe it's called falsifiability, which is the idea of, having a hypothesis which is capable of being tested to check whether it can be falsified. And if it can be, then you don't necessarily throw it away because it might be handy to describe limited circumstances, e.g. Newtonian mechanics over Einstein relativity ideas. That was all I was going to add.
Okay, just a technical comment. Somebody has music on, so we should mute that. It's either music or feedback. I'm not quite sure which. Okay.
Like a radio.
Okay, yeah, you'll have to mute that. Okay. Unfortunately, you people, I know that it's not voluntary, but you're moving around on the screen, so it's a little hard to follow whose hand is up. But Martin.
Yes. Well, from what I understand, you start with observations within a system, and you have a series of observations, and based on that series of observations, your interest is in predicting future observations. So you build a hypothesis. Then with that hypothesis, you do a trial prediction of observations. If the observations in the future adjust to your hypothesis, you have a good hypothesis and you continue with that and try to refine it. Otherwise, you adjust your hypothesis so it predicts more accurately the future observations. And you iterate through that process constantly, striving to get the best possible predictive value within your generated by your hypothesis. And to me, that is the essence of the scientific method.
Oh, let me just add in people's answers, if you can address sort of what is not scientific method, or what is the contrast that Alfane in particular is making about what he considers
Yeah,
the
not
Ptolemaic method.
yeah.
Elliot and then Ron.
Oh.
Yeah, I think, going off of the point about prediction, I think we're looking at our observations to see what kind of patterns we can detect, and therefore we find correlations in nature between causes and effects, because we're mostly interested in understanding how do these effects arise. And the challenge there is really to figure out how we test our notions of what may be the cause for an effect, so that we can move from a correlation under just simple patterns of correlation to an understanding of the causal mechanisms in nature itself that bring about this relationship.
Okay, and Ron.
Okay, I'll be a bit contrary. Two things. What is it not? It's not the modeling. It's not just using numbers and thoughts, as Einstein said, his great thought experiments. They're all well and good, but they don't necessarily model reality. What we're trying to do is model the real world and understand the real world. Another issue I've always had a bit about what is research, because I've been engaged both in scientific research and in computer graphics, and they're quite different beasts in a way, because you don't form hypotheses when you're trying to solve a problem in programming. It proceeds in a different way. You're still trying to understand and do something that hasn't been done before and make a better model of reality. And so it is a model in that sense. So making models isn't necessarily bad, provided they're useful and correct. And at least in computer graphics, you could tell it was correct because the picture looked right. If it didn't look right, it wasn't correct. So you've got to have some basis for deciding right or wrong too.
Yeah, let me just chip in something here, because one of the elements that I tried to emphasize in the chapter you read, chapter 3, is that one part of the scientific method that wasn't emphasized when I was in school, and certainly as part of the method, and certainly isn't really in the definitions up until Ron that you mentioned, is technology. Is that the actual usefulness of science and the ultimate test of the truth of science as a description of nature is its implementation in technology. I mean, I remember I had this discussion with a cosmologist who we had been at a workshop together, and we're at the airport, and he was putting forward the thesis that really science was just, one way of looking at the universe, religion is another way, there's really no way of saying which is true in an absolute sense. And I said to him, well, you know, if that's what you truly believe, I really wouldn't recommend taking the next step and getting on that airplane, because the only reason that that airplane, I can have any confidence that that airplane is going to get safely to the other side of the ocean is that aerodynamics is true. That the truth of aerodynamics is demonstrated in the fact that we can make airplanes that reliably fly. And I think that that's one thing that's very left out of most descriptions of the scientific method, is that they don't get to the point that the ultimate verification, the ultimate usefulness of science is our own survival. That science doesn't start just from professional scientists. It started a long time before that. You know, when our ancestors were saying, well, you can eat this mushroom, but you better not eat this mushroom because it made me really sick. That sort of accurate description of nature allows you to make predictions about the future, predictions that if this action happens, then this action will happen. That actually can aid your survival. Okay, so Tris has not spoken. Go ahead.
Sorry, my camera's being weird. I just wanted to try to speak to the Alphen bit. If I remember and understand correctly, the contrast with the Ptolemaic method is that whereas it sounds like we in this moment are describing science as something that like takes observations as a starting point and then creates theories from those observations and then uses those theories to make predictions, as you just discussed. The Ptolemaic method, it seems like, did the opposite. It had this really extravagant, you know, concentric spheres or whatever theory, and then it took observations about the stars and it fit those observations to the theory rather than fitting the theory to the observation. So that seems like the contrast that Alphen wants to make. But I am also interested in these points about the necessity of modeling and the efficacy of technology, because I think it might be too soon for this, but I think that the more we dig into those points, we might see that this dichotomy that it seems like Alphen's trying to draw between prioritizing observation and prioritizing theory doesn't actually hold up to scrutiny as much as we might think it does.
In what way?
Well, in the sense that observation itself is always theory laden, I guess, to be brief about it.
Okay, Sam, and then
Yeah,
Carl.
just to respond to the point about observation, I think that's where like technology makes the difference, because observation can be very theory laden until you make a machine that flies through the air, and then we can fly. And it's like that is like a material difference that separates theory from observation when it results in like quantifiable results and like improvement of life.
Carl, unmute. Carl, unmute.
Okay. I think one thing that's left out of all of this is the social context. And that has to be put in because in the very, in early societies, religion so dominated everyone's thinking, you couldn't question the basis of any scientific question. You just couldn't raise that issue. So I think you have to incorporate into maybe the scientific method the social context in which people are trying to understand nature. I think that's a really, really important issue, and no one teaches that.
That's true. And we'll get into quite a bit in the course, I think, in the course of our discussions, what, you know, people have talked about, you've read about in the newspapers, the politicization of science. But I think that it really goes a lot beyond the narrow conflicts about vaccines and so on. And I think that we can really trace that pretty far back into certainly over the course of the last century. But I want to emphasize one thing that nobody mentioned, which to me was very striking in Alphane's work. In one of the key things that he emphasizes is that real scientific method is a step-by-step method. The idea that hypotheses come from observations and are only valid if they can be tested, if they make predictions that can be tested by observations. And the thing that he wrote that had a great influence on my thinking is this quotation: to try to write a grand cosmical drama leads necessarily to a myth. To try and let knowledge substitute ignorance in increasingly larger regions of space and time is science. So he's contrasting the idea that of this step-by-step expansion of hypothesis and observation, which of course also interacts with technology, because as your technology improves, you can make new observations, make new hypotheses that allow you to develop new instrumentation. And certainly in the past year, we've had a great example of that with the JWST, which itself, the telescope, is the product of an enormous sequence of scientific and technical advances, but in turn has given rise to new observations that have a big impact on our view of the universe. He contrasts this with the idea that we can jump over the observations and by pure reason develop what the universe must be like. And, you know, before we sort of scorn this as what, you know, Ptolemy developed, which now is actually 2 millenniums in the past, even though people were still fighting these theories much more recently. It's a very seductive idea. And I must confess, I was very attracted to that method in my own development. I mean, you did have people with the prestige of Einstein basically saying this is how he arrived at his theories. Now, you'll see in another part of my book that, judging from his own writings, his description of how he arrived at his theories is quite ambivalent and a little self-contradictory. But one of the attractions is it's, to the scientist or budding scientist, it's very flattering, because it basically says, if you're smart enough, you can just figure out what is happening just by looking at what is the most beautiful logical theory and skip over the hard intermediate stages. And until I started actually reading Alphane's work in detail in the period leading up to the writing of my own book, that distinction really wasn't very clear to me, because obviously, like anybody trained in science, I knew that simply making a mathematical hypothesis like Ptolemy's and then sticking to it, no matter what the observation said, that was wrong. But what Alfvén is also criticizing is the much more widespread tendency to say, well, when we get to questions that are basic to physics, basic to our understanding of the universe, or to our understanding of things at the microscopic level, we want to develop an all-encompassing theory. I mean, the sort of self-parody of this people have heard of is the quest for the theory of everything that will describe everything in the universe. But even within physics, it's a real temptation to say, okay, we can jump by pure reason. And I'll give an example from my own research during my earlier, my first few years of astrophysical research, in which I used in a paper Dirac's large number hypothesis. Now, I don't expect people to know what this is, but Dirac, who is one of the leading scientists in the development of quantum mechanics, noted that there are two very large numbers in the study of physics and cosmology. One is the ratio of the gravitational force on elementary particles, such as on the electron, and the electrical force. So if you take an electron or proton and you calculate what is the gravitational force, you calculate what's the electrical force. Ratio is a huge number. It's about 10 to the 40th. So that's a trillion, 10,000 trillion, trillion. And we have some real world experience in this every moment, in that, you know, the force of my fingers, a very small object, which are exploiting electrical forces within my muscles, can lift this pencil, even though the force of gravity by the entire Earth, a vastly larger object than my fingers, is pulling it down. So that's one large number. And then another large number is the ratio between the scale of the atom and the scale of the universe, or the scale of phenomena in the universe, for example, of the Hubble redshift. And that also is about 10 to the 40th. So he made a hypothesis that these numbers must be equal, and therefore you can derive certain physical theories from this. Dirac does have a lot of prestige. So in this article, I simply said, well, let's hypothesize Dirac, then you can derive these equations. Well, there's a big problem with that. The big problem is, why? Why, other than pure reason, should we say these two big numbers are equal? As somebody back in Dirac's time said, what's so special about big numbers? I mean, you know, they're special to us because we don't usually deal with big numbers, but, you know, they don't have any intrinsic value as compared with small numbers like 3 or, you know, 3.14. The problem is we're not relating it to any physical mechanism that we can observe in nature, that we can deduce from nature, and that we can test with observations. So this is one thing that we'll get into a lot in the development, especially of 20th century physics, in which this jumping over phenomenon really interferes with the real scientific method. So we're going to be getting back to this, but I do want to get on to the second question, which is going to be, again, we'll be returning to. To a certain extent, the readings don't go into this very much, but since we're going to be studying the evolution of physics, I want to ask the question, what is physics? You know, what distinguishes physics from other fields of scientific study? So I'll open that up to discussion. Okay, Ron?
Well, I've always thought that physics is the study of that which is evident through the five senses. So it's all the physical things in the universe. It's been called the queen of the sciences rather than the king. You know, maths is supposed to be the big god of science, and then physics covers everything. Chemistry, biology, all of them are subsets of physics, whereas physics is a subset of mathematics that deals with the physical universe and only the physical universe. So it leaves out the the supra-physical, the ghosts and the goblins and the demons of the mind.
Right. Kathy, you're a biologist? Kathy?
I'm not.
Oh no, I'm sorry, Annette. Annette, you're a biologist.
I am an epidemiologist, but when I think of physics, I think of forces. I think of studying various forces and how they act upon objects and how objects act upon each other.
Do you think biology is included within physics?
I think physics isn't, yes, I think physics can be used to explain biology. I mean, I think physics is I think biology is on top of physics in a way. Like physical, physics phenomena are part of biology.
Right, but we do have the field, the subspecialty biophysics. So that sort of implies that not all of biology is the realm of physics, right?
I mean, I don't know that much about that subspecialty. I guess I'm not quite sure what your question is.
The question is what, as I say, the basic question is, what is physics? What distinguishes physics from other parts of science? Because
and to me, what I think of is the focus on forces in physics.
Okay. Okay. All right. We'll take a few more and then I'll comment. So, Peter, Tris, Martin, and Sam.
Yeah, very quickly. I fully agree with Ron. It's all about describing the physical entities of the universe. And I think perhaps the answer, it was a bit of a fast ball, I think, there. But the answer to what in biology isn't physics is possibly the philosophical side of biology, which isn't to do with physical phenomena in biology.
Tris?
Yeah, my inclination is to say that physics is like methodologically distinct from the other sciences. Like on the point about observation versus theory, I don't know enough about, like you mentioned, biophysics. I don't know enough about if there are if there's observational confirmation of this idea that like chemistry is explanatorily reducible to physics, and then biology is explanatorily reducible to chemistry. Like I know that's the way people sometimes like construct these disciplines, but I don't know if there's actually like observational evidence of that. And in the absence of that evidence, to me, it seems like physics is a science that I think, kind of like Annette said, prioritizes like mechanical or mathematical descriptions of physical bodies interacting with each other as a methodological approach to studying the natural world.
Martin?
Yes, I think that physics deals with the building blocks of the universe and provides a framework on which everything else is built. So chemistry is built on the framework of physics, and biology is built on the framework of physics and chemistry. I think physics is foundational.
Right. Well, a lot of physicists think that, that's for sure. Okay, Sam.
Yeah, to add on to that, I was gonna say, like, I mean, physics is like how big things and little things like move around and like communicate and interface with each other. And then other sciences sort of emerge from that as like an emergent phenomenon, where it's like little things forming together bigger systems, and then the bigger systems form their own sort of complex behavior. And those new complex behaviors need their own branch of science to study.
Right. Well, we're certainly going to be getting into that a lot in as we go forward with the history of physics, because really we're discussing, in a way, two different approaches, not only to the relation of physics to the other branches of science and what physics is, but even, again, alternative ways of looking at how to do science. Because the popular concept that you can explain biology on the basis of chemistry and chemistry on the basis of physics, and therefore you can explain everything on the basis of physics, is basically the reductionist view of science and the universe. And it is a very popular and well-defended viewpoint. The other viewpoint that certainly has also been developed a lot over the past century or more, that Sam referred to, is the idea of emergent processes. It actually looks at the universe in a different way, as consisting basically of processes that we have to understand, not things, and that processes emerge historically out of evolution at different levels that have to be studied with different tools and with different hypotheses. As I said in the announcement of this study group, there's going to be a complementary lecture series, a video lecture series called The Physics of Evolution, in which we're going to get into up-to-date concept of both the evolution of physical universe and here on Earth of the biological system. And that'll get into a lot of these debates. But, you know, it's interesting because preparing for this class, I actually looked up what is the definition of physics on the internet. And there are essentially two main definitions. One is similar to what Annette was talking about. Instead of physics is what deals with forces. It's that physics is the science that deals with matter and energy. And the other is the idea that physics deals with the most fundamental or elementary processes in the universe. But I think that if you actually look at what physicists are doing, there's a lot of contradictions in both of those definitions. In the elementary category, you sort of have to ask, well, what happens to biophysicists? I mean, there is a discipline of biophysics in which looks at certain aspects of biological processes. I'll get in a second what I think those aspects are. Biology, obviously, we all know, is not the simplest subject. Biology today is the product of billions of years of evolution, and these biological systems, down to the smallest bacteria, are extremely complex systems. So if physics is only the study of the most elementary systems, where does that leave biophysicists? And the problem with the concept that this is the study of energy, there's certainly aspects of that that are true. It's very difficult to study physics without simultaneously studying flows of energy. But energy and its transformations is extremely important in both chemistry and biology. It's very difficult to understand chemical reactions, any chemical reaction, without understanding where energy is flowing in the reaction. And the same with most biological processes. So I'd actually, I was thinking, how would I describe physics? I think physics in present practice, and we're really describing a sociological concept. I mean, you go back in history before, let's say, certainly before the 19th century, there was no such thing as physics because all of natural science was natural philosophy. So we're actually saying, what do physicists do? That's physics. And I think what is characteristic is physics is the study of phenomena that can be most easily reduced to relatively simple mathematical descriptions. If you look at things like biophysics, you're isolating the parts of a complex biological system that can be reduced to relatively simple mathematical description deriving from the laws of electromagnetism, our understanding of how atomic physics, molecular physics works. And certainly, if you look at what happens when physicists both basically have to engage other disciplines, it's really where the mathematical complexity becomes impossible. And we, for example, we know that quantum mechanics has been extremely successful at describing some of the basic phenomena in chemistry. But beyond very simple molecules and very simple atoms, you have to call on the body of knowledge that is chemistry. You can't, in practice, describe all of this in quantum mechanical mathematical terms. So I really think that in practice, physics has separated itself from the other disciplines, or the other vice versa. Disciplines separated themselves in the course of the 19th century, really on the basis of that idea of mathematical simplicity. So I'm going to throw that out for discussion, whether people think that is a workable definition. But second of all, I do want to, because we're going to be getting into the relationship of physics and mathematics, say that one thing that I think the mass media really gets very unclear on, partially because of what some physicists and mathematicians say, is that mathematics is a description of science. It is not science in itself. One of my favorite books that I recommend is titled Number, the Language of Science, which the book is a history of mathematics, and it emphasizes mathematics, like the English we're speaking, like other human languages, is a language. It's a way of symbolically describing nature. And just like I can say things that are true, or I can say things that are completely fantastic, mathematics can describe things that are reflective of what occurs in nature or completely unreflective. So with that caveat, let me just throw this out and say, what do people think of defining physics as that part of natural science that deals with the phenomena that have the simplest mathematical description? Does that work? Does that really describe what physicists do? Okay. I am going to ask people who haven't spoken so far to try that. Kathy, what do you think?
Sorry, could you repeat the question?
The question is, you know, I think that most of the definitions I've read of physics are unsatisfactory and don't really reflect the practice of physics. So I'm putting forward a definition of physics, as far as I know, it's my own, as the part of the part of natural science that deals with phenomena that can be described in the most simple mathematical terms.
Oh, so I actually so I was a little confused about like the difference between the physics and also the study of the cosmology, because they're definitely like overlapping, but yeah. So I mean, maybe in the future, what we know about physics may not be, you know, maybe truth. Maybe we'll have something completely unexpected, you know. So there's so many things that cannot be explained by the current physics.
Well, that's certainly true. But again, as I say, let me just try to briefly, before we go on to we are going to get into the actual history later in the session, but let me just respond to that as a tentative definition. Who had their hand up? Oh, Sam.
I was just gonna maybe like it when we were talking about sort of like physics as sort of like reducible down to the simple mathematical formula. It reminded me of like in programming, you have ones and zeros, and that's just like binary code, and that's the language of computers. But at a certain level of building an application, it's too complex to be writing your entire software just typing out ones and zeros. So you need to have a higher level of abstraction, sorry, that become more simplified languages on top of like the really complex model of binary code. So you have like Java or JavaScript, which is like you're writing English, but really you're writing ones and zeros underneath. So maybe that's an analogy between like when I'm doing chemistry, I'm like really doing really super complex physics under the hood. But I'm like, I don't speak physics. So but I speak chemistry. So I'm going to describe it in chemistry terms. And not just programming. I feel like that's an analogy to languages in general. Like at a certain point, language, like human language, is just sort of like grunting and like making noises at each other, and that's like expressing like really base level emotions. But like sometimes we have ideas that are too complex to articulate in grunts and noises, so we have to use words and sentences.
Yes.
Yeah, I wanted to respond to your like third definition of physics, the idea that it's the study of those aspects of nature which are most readily representable by math. Well, I guess sorry?
By the simplest math. It doesn't mean that it's necessarily simple, but simplest. Yeah.
Gotcha. Okay, well maybe because I wanted to ask you about that, because on the one hand, that seems like a really strong definition. Like it lends itself well to the sort of methodological lens that I like to take on these sort of things. And I like that it's rooted in the actual practice of physics, like you said. But I'm curious how you would distinguish like other fields of study that are also heavily reliant on math. Like it seems like you wouldn't want to say that economics is a branch of physics per se, but economics uses relatively simple mathematical modeling. So I don't know, on the one hand, like I really like that definition, but I'm curious about how you would like specify the domain of physics, if that question makes sense.
Okay, well, I'm going to go around the room before responding. So Carl, and then Peter, and then Ron. Carl.
Well, I was thinking that if you relate physics to just because it can be written in mathematical terms, that becomes really problematical, because when you're thinking of plasma and electromagnetism, that's such a complex mathematical relationship, because, you know, the electric field changes the magnetic field, and then the magnetic field changes the electrical field. It becomes, you know, that's so complicated that you can't express that totally in mathematical terms. So I think I would prefer a definition of physics and that it relates to sort of basic particles and how we understand basic particles and their reaction, and maybe leave out the mathematical aspect of it, because that's what's led us into all these problems, you know, in the crisis of cosmology, that people are just looking at mathematical models and not relating it to the reality. So maybe we have to separate out the mathematical aspect of it from physics and look at another definition. That's my thinking.
Peter. No, I'm mute.
Could you just say your definition once more, please?
My definition, and by the way, this is something that I thought about over this isn't something that I've developed over a long period of time. This is something
okay.
I thought about over the last 2 weeks. But my definition is that physics is the part of natural science that deals with phenomena that can be described in the simplest mathematical terms. So
Yeah, no, that's fine.
That would be what was distinguished that.
I think you still need the physical, you need to have the word physical in there somewhere, don't you? Because as was previously said, you could otherwise, you wouldn't be able to distinguish. Economics was the example given, which is quite a good one. Economics would be included in your definition, wouldn't it?
Well, most people, again, remember, we're describing in effect sociology, what scientists do, and in distinguishing between what people do, most people would not include economics as a natural science.
No, what I'm saying is,
In other words,
conversely,
I
if
said
you're presented with some
that
economics,
this is the part of, generally people, the natural sciences, well, we'd have to describe the natural sciences too, but the natural sciences are generally distinguished academically and otherwise from the social sciences. So economics would be part of the social science, physics, chemistry, biology, geology would be part
nevertheless,
of the natural
the
science.
problem is if you present somebody with a bit of economics and tell them it's physics, with your definition, you wouldn't be able to say, no, it's not, would you?
My definition is that physics is the part of natural science. Economics is not, by most people's definition, a part of natural science. Again,
Okay,
we're not talking about rules of the laws of the universe. We're talking about how the actual division of labor among academics, scholars, whatever, is. So
okay. Maybe it's your turn of phrase natural science, which I hadn't. Yeah, maybe that is a substitute for physical. Is that what you're saying? Why not use the word physical?
well, no, I mean,
Why not add it in? You know, because then it's clear. Because physics is about the phenomena.
I mean,
of-
it isn't, because, I mean, I'm hesitating because I haven't thought much about what the definition of natural science is. I mean, again, in practice, if we look at how things are divvied up academically, it seems to me it is by exclusion. In other words, the social sciences are the study of phenomena that involve human beings.
Yeah.
That natural sciences, I mean, then
Natural sciences are about the
and then
natural
of course
world.
we'd get the psychologists mad at us.
Well, natural science is about the natural world, and that includes all of biology. It includes a lot of other things as well.
Right, but I mean, the contradiction is, and I'm not saying that maybe we have to put aside this question and think about it. The contradiction is we have an academic division between the humanities and the social sciences on one side and the natural sciences on the other. And the social sciences could be defined positively as sciences that involve the study of human beings and their actions.
Yeah. I would just add the two words physical.
Are part of the natural
phenomena.
universe. It gets into problems with parts of the natural sciences, neurophysiology, psychology, and so on, that do study human beings. So, future discussion, but I think that, clearly there is a distinction. Now, this would get into a big argument, but I'd also argue that much of what passes for economics does not qualify as science by the definition that we just dealt with, that it doesn't use the scientific method of, testing against predictions. But that's perhaps a whole nother argument. But I see what you're saying is that if you're making this definition and using physics as part of natural science, you have to define what natural science is. I certainly have to think a little bit more about that. I think Ron was next.
Yeah, the problem with mathematics, as you started off saying, is actually just a precise way of saying things. It's just a form of language ultimately. So it it's just language, precise language. Now, saying simple mathematics, you're saying you keep the math simple. So you're hinting at Occam's razor. That is, the simplest solution in physics is going to be the best. The reason why you use...
I'm not saying that, but go ahead.
Well, that's what Occam's razor does say. And generally, I think that is accepted. If you've got a number of different ways of describing something, the simplest explanation is the one that most people will then go with, because it's easier to understand, simply. But the problem that why you use mathematics is because you need to be precise. You need to have the same definition of terms amongst all the people. And that trips people up all the time. If I say God and you say God, we might be talking about two totally different things, and we get into a big argument about it. And then 3 weeks later, we realize, oh, hang on, our definitions are different. So you need to precisely define things. And that's, I think, why you're using maths to define physics. Am I right or wrong?
Well, as I say, we're really talking about sociology, in the sense we're talking about what distinguishes somebody who says this is a physics course and what distinguishes somebody who says the chemistry course. I think that we're going to see how physics developed and get some better idea of what the definition of physics is as we get into the history, which we're about to do. But in terms of mathematics, I want to address your point and the earlier point that was raised, I think by, well, I'm not sure, I think by Carl, about complexity. I mean, there are two things that distinguish mathematics from other languages that human beings have developed. One is exactly what you just said, is that mathematics is structured so it's intended to have precise definitions. Many, many years ago, our ancestors developed the idea of numbers. In other words, that two antelope have something in common with two stones, so the number 2. But eventually, it developed a precise definition that everybody could agree on. So that's one thing. There's another big difference that makes mathematics very useful for the sciences, is that mathematics does not admit of self-contradictory statements. A proof or a disproof of a mathematical statement is precisely to either demonstrate that it is logically consistent with the rest of mathematics, or there is a logical contradiction. So it's never possible to say in mathematics that X is true and not true. Now, we know from, people may have heard of Gödel's famous proof, that there are statements that we can never prove or disprove. So we don't know whether they're true or not, even though they're mathematical. But we can never accept as part of mathematics statements that we can prove are self-contradictory. But clearly that's not true in English. I mean, we could say of fill in the blank with your favorite politician or other public figure, well, this guy's an idiot, but he's not an idiot. That's a perfectly good English sentence. Most of us will know what the meaning is, but it's self-contradictory and it would not be allowed in mathematics. So that's a second very big difference. I wanted to address the point about complexity of description. Plasma physics is a very complex, we are looking at complex phenomena, but they can be described by relatively simple mathematics. Maxwell's equations describe a great deal of what happens in plasmas, just with the addition of the description of the nucleus, the electrical properties of nuclei and of electrons. There's a big difference between saying these can be described by simple mathematical formula and saying the phenomena themselves are simple. As I am fond of saying, Maxwell's equations are easy to write down. They're actually easy to understand, and we'll be getting into them in a fairly near study group. But they're extremely difficult to solve in any realistic situation. And that's why plasma simulations are mostly very difficult and generally very poor descriptions of what actually happens or predictions. So there's a big difference between having mathematical descriptions of a phenomena be simple and the phenomena themselves be simple. They can be extremely complex. Well, we don't need to resolve this question, fortunately. So what I want to do is go on into starting with the historical material. And the readings I gave my own chapter 3, to give a general background. Many of you know this, of the broad development of science during the centuries after the, ultimately after the collapse of the Roman Empire, and especially accelerating with the Renaissance in Western Europe. But I gave the Faraday reading because that's really where we're going to start our history of physics, which is where most high school physics has already ended, because most high school physics doesn't get out of the 18th century. With Faraday and with the rapid discoveries about electricity and magnetism in the early part of the 19th century, this is getting into what we really call modern physics, and which is the basis of our entire technology. So based on the readings, I wanted to ask a couple of questions about Faraday. First of all, from what you know and from the readings, what is the huge shift that Faraday made in our understanding of electrical and magnetic phenomena? Why does the study really look very different after Faraday than it was before? Okay, Ron again?
Got to be quick, don't you? He unified the electrical and the magnetic fields. He showed that they're always present together, and his 4 equations actually link those fields together.
Well, isn't that Maxwell's equations, though?
Oops.
I'm talking about Faraday.
Oops. Oh, well, I'm getting old.
They are closely related individuals, but anyway.
Faraday,
No, I'm
Faraday.
talking about Faraday.
Oh, he's homopolar motors. He's the homopolar motor guy, isn't he, Faraday?
Right. Well, did people do the, I gave a little reading that was an Encyclopedia Britannica article on him. Did anybody read that article?
Yes, I read it. I got diverted because underneath was a description of Einstein's life, and I got very into that. That was absolutely amazing.
Oh, you got diverted within Britannica.
I did.
I see. Okay. See, this is the dangers of reading things online. If you had been reading that hard copy, you wouldn't have gotten diverted.
Was it something about how Faraday discoveries about electricity led to new discoveries about like chemistry? Did it lead to like the birth of chemistry where like electricity can cause molecules to fuse together?
All right. Well, maybe the reading wasn't sufficiently engaging. I was trying to find. Well, let me take a step back. I mean, Faraday was both an extremely pivotal person in the development of physics and a very interesting character, because he started studying at a time in which the natural sciences, the study of the natural sciences, were overwhelmingly pursued by people who came out of, the elite class in England and on the continent. And he was anything but. He was a working class kid because of his father's health difficulties. They were often on the verge of starvation. And he started to self-educate himself when he became apprenticed to a bookbindery. So he took the opportunity, of course, books is the earliest years of the 19th century. Even though books were published on a mass scale, they tended to be still pretty expensive from the standpoint of the working class. This was a period in which the working class wages were extremely depressed. There was a process of forcibly removing people from the rural areas, forcing them to move into the cities. That created conditions for very extreme exploitation. The life expectancy in many of the British cities in the early part of the 19th century dropped into the teens. So he had access to these books because it was a bookbindery. So he managed to learn to read, and he started to self-educate himself. And this was during a period in which there was an impetus to popularize science, because as British industry developed, there was a necessity to develop a class of skilled workers who had knowledge of the new science that was developing. So in the period well before radio and television, you had public lectures. So he attended a public lecture of Davy, one of the leading scientists, series of public lectures. He wrote up his notes on these lectures, bound them into a nice volume at the bookbindery where he worked, and presented it to Davy. And indirectly, this led to Davy hiring him as a lab assistant and the start of his career. Tris, you have your hand up? Or you just forgot to put it down?
No, yeah, I just wanted to try to take a stab at, you had asked earlier, like what Faraday's contribution to our understanding of electromagnetism is. If I remembered and understood correctly, it seems like there's basically two things, both of which make him, like, in a weird way, maybe sort of analogous to Newton. Like, and the one thing that he did is he unified all of the different manifestations of electricity that we knew were a thing in the 19th century. Like in the same way that it was sort of revolutionary for Newton to say that the reason things fell on Earth was basically the same reasons the planets moved around. Faraday was saying that, like, the reason, like, the new electrical generator that had just been invented worked was, like, the same reason, in a basic fundamental sense, that, like, lightning worked. He, like, unified all these different instances of electricity, which we now think of as being the same thing. but in the 19th and earlier centuries, people didn't realize that they were all the same thing. And then the second thing, if I understand correctly, is that people thought that maybe whatever these electrical instances were, they were maybe some kind of fluid or some kind of like, I don't know, material substrate. But then again, similar to Newton, Faraday introduced this new kind of force, this new kind of like unified, and now we think of it as a field, right? But it seems like those were the two novel ideas, was that one, all manifestations of electricity were the same thing, and then two, that they were all the same force specifically.
Well, I think that you touched on the key thing. I'll get into that in a second, which was the term field. Let me just, again, briefly give this background, since I don't think everybody did the reading. Is he initially studied chemistry, and we won't go into it, but he made some fundamental discoveries in chemistry. He did not, because of his lack of formal education, Faraday did not have a strong background in mathematics, but he had a very good concept of the scientific method as the experimental method, determining things, answering questions by experiment. So with his background in chemistry, he started making big discoveries in electricity and magnetism. And the first of these discoveries was coincident with his invention of the electric motor, which was that based on Ampere's earlier discovery, Ørsted's, that a electric current could produce a magnetic field. He showed that an electric current can actually move a magnet in a circle. He also discovered that the contrary was true, that if you have a conductor, and I think it was Ron that mentioned the disk generator, conducting disk rotating in a magnetic field, that would generate electricity. So he was the inventor both of the first electric motor and the first dynamo, changing electricity into mechanical energy and mechanical energy to electricity, which obviously, again, is at the foundation of all of our electrical technology. We use motors that are based on that principle and dynamos throughout our technology. He had, from an early time, this concept that Sam mentioned, that electricity was probably not describable mainly as a fluid flowing from one place to another, although there are actually lots of aspects that do make a good analogy between fluid flow and electrical flow. But from an early stage, he developed the idea that this was a wave phenomenon, that something was oscillating back and forth. And one of his famous experiments was that he had a battery with a switch and a magnet. And when he put the switch so the electricity turned on suddenly, he saw that not only could he induce the magnet to change its direction, that in another experiment, he could induce a flow of electricity in another wire. And then he turned off the experiment, but being a good experimentalist, he noticed that when, to his surprise, when he turned off the current in the other wire flowed in the opposite direction. So this, again, gave him a clue to a wave nature. I won't describe, I'll try for next time to get better readings on the whole course of his investigations. But over the course of decades, he developed the basic concept of the magnetic and electric fields. And he actually coined that term as the jargon use that we now have of it. Although interestingly, and I read this from a historian, he never defined what a field is. We'll get into that in just a second. What he found was people had known from a long time that if you take iron filings and you take a magnet, the filings will line up in lines. And if you take any magnetized thing and you put it in the same place, the magnet will align in the same direction along these lines. Now, what he came up with was the idea that these lines were not simply a description of the force that a magnet was applying at a certain spot in space, but this was a description of a characteristic of space itself. And that was the big breakthrough conceptually. Because remember, if we go back to Newton, Newton's basic hypothesis was that you could describe physical behavior and physical forces precisely mathematically by assuming that isolated particles, such as gravitating bodies, are acting on each other according to mathematical laws that had high predictive value, but he did not hypothesize how this occurred. It was the famous Latin phrase, hypotheses non fingo. I don't make any hypotheses. He said, I don't know what gravity is. I'm not going to guess. I don't know what happens in between this point and that point. One point he gave a purely religious. He said, God causes them to move this way. So going into the 19th century, full century after the work of Newton, you still basically had this idea of particles. And by that time, chemists were developing the idea of atoms, originally dated to ancient times. Particles influencing each other through empty space. And Faraday's huge breakthrough was to say, no, there is a field, there is a property of space itself that conveys the magnetic and electric behavior from one object to another. So what he showed was that at every point in space, you can describe what we would today call a vector. You can describe a direction for the magnetic force and an amplitude for that force, and the same with the electric force. And these operated in ways that were not the same as gravitation, which was point to point, but actually, in many cases, that they would cause rotational motion rather than point-to-point motion, direct motion. By the time that he had developed this concept fully and presented it, he was actually 60, which is a good example. I'll point to these other examples of contradicting the modern notion that physicists do their best work before they're 30. But this had a revolutionary impact. mean, by this time, he was a very well-known scientist. So the steps he had taken, the development of the dynamo, the development of the electric motor, had already been integrated into technology. By this time, and I'm talking about 1850, 1852, of course, you had a massive shift in technology by the development of the telegraph. And the telegraph used this basic idea that you could control the conduction of electricity over long distances. And remember, with the telegraph, back in the early first half of the 19th century, you had the first development of instantaneous communications. It wasn't until later that they could be across oceans by the cables, but within continents, you had the development of instantaneous communication, which was a huge shift because before the telegraph, communications, of course, in general traveled no faster than a horse. So that field concept is central to the further development of electromagnetism. So let me just I mean, I've sort of said what a field is, but let me ask what your understanding. What is a magnetic field? What is an electric field? What does that term mean? Okay, I do see his hand, but I've lost your name. Dan.
First, I just wanted to say I don't think I got the reading on Faraday, but to try to answer the question of what is a field, I guess it would be some sort of influence that an object puts out that goes beyond its direct spatial extent. That's the only way I would know how to describe it.
Ron?
I think it's always been very problematic to me because it's a mathematical description of the electromagnetic field from point to point. The problem is it doesn't give you any understanding of what electricity or magnetism is. How can something be or move through nothing? You know, the old ether versus the relativistic arguments. I've always been a believer in the ether, sorry. Nothing can move through nothing. There's something there. But, you know, that's an argument for another day. So it's basically just a mathematical description of the electric and the magnetic field at every point in 3D space.
Well, anybody else? Sam.
Yeah, I was just gonna say it. I think of it like a field is like a bunch of lines in 3D space. And those lines all sort of have points upon them, which also have a bunch of lines pointing out. And everything in the world sort of gets pulled along by them and like influenced by them. There's probably a smarter way of saying it. But like simply, I don't know.
Okay.
Yeah.
Peter, and then Martin, and then I'll comment. Peter, unmute.
Blast. I just agree with Ron again, except I would say that it describes how the subject of the field, e.g. if it's electrical field, how an electrical charge is impacted in a certain place in space and time whilst in space.
Right. This is in reference to how objects behave, and that's how it is actually measured. Martin?
Yes, I conceptualize fields as distortion in space-time that result in a potential energy gradient.
Well, let me again go back to what Faraday intended. And I recently read one of his rather long essays. This is the 19th century. People didn't care about attention span, in which he describes his own evolution. And his evolution was absolutely aimed at the question, is this simply a convenient mathematical description of a phenomenon? Or is this something that really exists in quote unquote empty space? And the big transition in his thinking was to say there is something that really exists, that a magnetic field is a real object. And that was a big revolution, because from the Newtonian time on, the concept was objects are basically atoms. They're isolated from each other. And his concept was there is something filling space, in theory, filling all space, which is a real physical object. Now, at his time, he didn't know this. Maxwell was the one who developed this. But we know today magnetic fields actually contain energy. I mean, I don't know how many of you follow our detailed technical updates, but one of the things that we did recently with our machine was increase the current that it produces by decreasing the amount of energy in the magnetic field outside of our device, in the switches. So the magnetic field contained energy that was where we didn't want it to be. We wanted to, as much of the energy as possible, to be inside our vacuum chamber producing fusion. So this was a radical new idea of what the universe was composed of. But it wasn't composed of just individual particles. And remember, Newton's theory of light was originally a particulate light. But there was a continuous something, continuous objects, describable, as Sam says, by a field of vectors that at every point describe the force that would be applied on a charge. The charge was moving at a given velocity. There would be formulas to describe force on a charge, a force on a magnet of a given strength. And that this field of vectors, very analogous to a field of wheat, in which you have lots of little strands of wheat pointing, of a given height pointing in a given direction. That was a real object. That was a thing. And that we could only understand electricity and magnetism by taking into account the physical reality of these fields. So it was basically saying, no, this space is not empty. It contains magnetic and electric fields. And as Maxwell later showed, these not only can exert forces, but they can contain energy, very significant amounts of energy. And the complete development of electromagnetic technology was actually totally dependent on the notion of these fields being real physical objects. So that's actually a good place to end several people had to drop off early, and I'm assuming people do have to go at 5. So I would like to devote a little time to structure questions. I want to get some feedback on, first of all, how often people feel these study groups should be, because I will be giving readings each time. It is a substantial commitment of time. It's 2 hours. So I want to get some idea, 2 weeks, 3 weeks. I couldn't do them weekly, so I suspect nobody else could either. Monthly, whatever. So, some opinions on that.
You probably need a voting system.
Well, let's just shout out.
Okay, I'd say 2 weeks.
I think 2 weeks too.
2 weeks.
I'd say 3 or 4.
I'm happy with 2 to 4.
Yeah, 2, 3, 4 is fine.
2 to 4.
All right. Well,
2 weeks. I'd say 2 weeks.
all right. Well, fortunately, since mathematics is so precise, I can average 2 and 4 and get 3. So I'm going to, it is notable that quite a few people did not attend. I don't know whether they will attend in the future.
How
But-
many people said they would, Eric?
What?
How many people said they would attend? Roughly?
It was close to my limit. In other words, I set in advance a limit of 24.
Right.
I think 20 people did sign up. And I think that we had, so we have,
We had 12.
we have 12 still on the call, but I think 3 people have left. But that's actually better. Actually, 15 is a little probably more optimal than 20 in terms of allowing people time to speak their mind. All right, so I hate to say it, I'm forgetting the other question I had for you. Well, I mean, it's a routine question, but I assume that this Saturday 3 to 5 is going to be okay with everybody going forward, right?
Sure.
Yeah. Bit early for me. 5 a.m. Never mind.
What?
It's a bit early for me. It's 5 a.m. in the morning. but
I
that's
know. Well, thank you so much. The two
Same here.
for
It's a bit late for
attending.
me.
I
It's
did
8
not-
to, 8
I
to
mean-
10 in the evening.
It's mathematically impossible to make a time that works for all 24 time zones. So I really appreciate this is not convenient for you guys. It is okay for the Europeans. So yeah, the other question is the amount of reading about right? Because
yeah, not too much.
it's doable. Okay.
Yeah.
All right. Well, I don't have the reading list for next time ready, but it will be ready within the next few days. So why don't we, so we do have a few minutes left. So in the last few minutes, are there any questions that anybody wants to raise about what we've discussed so far, or additional comments? Peter.
Can we just go back to, you said Faraday refused to hypothesize how it worked, how it all worked?
Newton.
I think that's what you said.
I said Newton refused to hypothesize what gravity was.
Oh, sorry. It wasn't.
Yeah.
It wasn't Faraday. Okay.
No, it was Newton was basically saying, I realize I am describing what later people called action at a distance.
Yeah.
And I'm not going to describe how this happens. I'm not going to make any hypotheses.
Can I just check?
How this happens, whether it's action at a distance. I actually found a quote from him saying, anybody who thinks that there's such a thing as action at a distance probably doesn't know the first thing about philosophy. But he did not say that he thought it was something other than action at a distance. He basically resolutely said, I'm not going to express any opinions on this. I'm only going to say how it's described mathematically. But
So my question was really, isn't that still the case then? He was right to not, that we then and even now can't actually say how magnetism, gravity, electrostatic force works. It's,
well,
we can do all the
obviously.
equations, we can produce all the laws, we've got all those, we can predict it to the nth degree, but we can't actually say how it works. Is that correct?
Well, obviously, as I say, with the different subject of electricity and magnetism are different forces. I think that we definitely have moved beyond what Newton was talking about, because as I say, our entire technology is based on going forward from Faraday's notion that magnetic fields and electric fields are things that exist extended in space, so that we've gone beyond Newton's. The Newtonian assumption was that the universe is basically describable as isolated particles interacting by mathematically describing laws. And what happens between those particles is, in Newton's view, we're ignorant of. And in most of the intervening years of science, in the Newtonian years, we can call it in the 18th century, it was assumed that nothing was happening, that this was truly empty space, a vacuum, even though people realized there was problems with that concept. So that was a basic concept of what the universe consisted of. In the case of electricity and magnetism, as we'll get more into in the next section, which will get into Maxwell, we do have a much clearer idea that there are physical things that are extended throughout space, that space is not empty, but there are fields that are physical objects. So in that sense, we move beyond it. In the case of gravity, yeah, we'll postpone that to when we get into the 20th century, Einstein's notion of gravity. But, to a certain extent, maybe you can say Newton was doing the right thing by not hypothesizing, because he probably would have gotten it wrong. Okay. Other comments? Ron? And then we should end up.
Not so much a comment, but just a great thank you to you, Eric, for spending the time to do this. You are obviously a very busy person with a lot to do, and I'm greatly appreciative of you spending the time on this.
Thank you all for doing the same, and do feel free to send me any comments on your impressions of this first session, things that can be improved. My email is just eric at lpbfusion.com. Okay. Well, thanks all, and either good morning or good evening or good afternoon to all of you. And we'll see you all in 3 weeks.
Brilliant. Thanks very much, Eric.
Bye-bye.
Cheers all.
Bye-bye, everyone. All the best.